Chemical reactions are continuous, everyday processes driving the changes we see in our food and our environment. In a laboratory setting, performing a reaction like burning a magnesium ribbon requires a specific first step. You must rub the ribbon with sandpaper to remove the protective, unreactive layer of magnesium oxide that forms naturally over time. We can determine if a reaction is taking place by looking for 4 specific empirical markers: a change in state, a shift in color, the evolution of a gas, or a significant change in temperature. When the fundamental identity of a substance changes, evidenced by these markers, we use a chemical equation to map that transformation. Every equation is governed by the law of conservation of mass. Because atoms cannot be created or destroyed, the total mass of the reactants must equal the total mass of the products. Take this skeletal equation for iron reacting with water. Before we balance it, we place locked boxes around each formula. The chemical formula inside these boxes is fixed and cannot be changed. Attempting to edit the small subscript numbers inside these boxes is a mistake because it mathematically alters the molecule. Modifying the subscript would mean you are no longer reacting water, but an entirely different substance. Instead, we use the hit and trial method. We track the atom counts in this table and achieve a balance by adding stoichiometric coefficients, the large numbers, only in front of the locked boxes. To complete the equation, we add the physical state symbols for each component, showing that solid iron is reacting with water in the form of steam. A balanced equation is the final mathematical proof that every atom present at the start of the reaction is accounted for in the products. We categorize these changes by their behavior. A combination reaction occurs when 2 or more reactants merge into a single product, like when quicklime reacts vigorously with water to produce slaked lime and a large amount of heat. This reaction is the basis for whitewashing walls. The slaked lime solution reacts slowly with carbon dioxide, eventually forming a thin layer of calcium carbonate. Decomposition reactions are the exact opposite. A single reactant fractures into multiple products. This process requires an energy source. In this first panel, thermal energy breaks down green ferrous sulfate prestals into ferric oxide and gas. In the second panel, we use electricity to decompose water. This results in a specific 2-to-1 ratio of hydrogen to oxygen gas, reflecting the composition of the original water molecule. The final panel shows photolytic decomposition, where light energy is used to break silver chloride down into silver metal and chlorine gas. Whether it uses heat, electricity, or light, decomposition is the active dismantling of chemical bonds. The reactivity series determines what happens when an iron nail is placed into a blue copper sulfate solution. Because iron is more reactive, it displaces the copper. The nail turns brown as copper deposits onto its surface, while the surrounding liquid shifts from bright blue to pale green. Double displacement reactions involve an exchange of ions between 2 compounds. This is often signaled by the sudden appearance of an insoluble white precipitate when 2 clear solutions are mixed. We track the movement of oxygen using the concept of redox. In this equation, hydrogen gains oxygen, which is oxidation, while the copper oxide loses oxygen, which is reduction. Oxidation and reduction are not solitary events. They are 2 halves of the same elemental exchange. These redox reactions have significant real-world consequences. Corrosion is a slow oxidation process that destroys structural metals, like the iron in this fence, over time. Tarnish is another form of environmental degradation. It specifically affects precious metals when they react with compounds in the atmosphere. In food, the oxidation of fats leads to rancidity. To prevent this, manufacturers flush food packaging with nitrogen gas to displace oxygen and preserve the contents. Use this grid to review the 5 reaction types. By mapping formula patterns to their visual triggers, like brown fumes or specific gas ratios, you can quickly identify any reaction. Understanding these visual triggers and mastering the box locking method for balancing ensures you are prepared for any exam scenario.